Hey, welcome back. Today we're talking about global extrema of multivariable functions, namely when they exist and how to find them when they do. Let's get started. So here's the question. If we have a function, let's say of two variables, f of x, y, when can we guarantee that it has a global minimum and a global maximum on its domain? Well, as we might have already seen so far in this optimization unit, it depends on the domain, meaning it depends on the set of inputs that we're considering for this function. Let me give you an example. The function in question is f of xy equals just x plus y. And the question is, does this have a global maximum and minimum on the following sets? One of them is the disk of radius 1. The other one is going to be the disk of radius 1 that does not include its boundary. So maybe we would call this one the closed disk of radius 1. We'd call this the open disk of radius 1. And the last one is going to be the first quadrant, which is where x and y are both non-negative. So I'm going to sketch those real quick. Okay, so these are actually three separate optimization problems, where we have a function which just takes two numbers and adds them together. And the set of allowed inputs are this disk here. This disk contains its boundary, or this disk here, which does not contain its boundary, or the first quadrant, which is where x and y are both non-negative. Now, I'll note that none of these pictures show anything to do with this function. If we wanted to, we could draw in the level sets of this function. Those would be lines that are parallel to the line y equals negative x, so they would be lines that are sloping down with slope -1. And maybe with that picture in mind, we can see that the maximum of the function on this set is going to be here in this corner. This is the max. And the minimum is going to be in the opposite corner, down here. And when I say maximum, I do mean global maximum. This is the largest this function is on the set. And similarly, this here is a global minimum. For this disk that doesn't contain its boundary, we can see that actually there isn't going to be a global maximum. It would have to be around here. But since this point on the boundary isn't actually in the set, we can get closer and closer to this point while staying inside the domain. And in doing so, we'd be making the value of the function larger and larger, but it would never hit a maximum value. In other words, we could always find slightly larger values of the function by getting closer and closer to this point here. And because this point isn't in the set, this isn't one of the points that we can plug into the function. So there isn't a global max. And by the same logic, there's no global min. It would have to be here, but this point isn't in the set. For this third example, if we're looking for a minimum value of this function, well, we're only considering inputs where both x and y are positive or 0. And if we're just taking those two numbers and adding them, that's what the function's doing, then the smallest that's ever going to be is 0. So the global minimum is here at the origin. On the other hand, for a global maximum, since this set contains arbitrarily large x and y, we're never going to have a maximum value. We could always plug in larger and larger values of x and y to find larger and larger outputs. So there's no global max. Okay, so in summary, if we're trying to solve an optimization problem, we're trying to find global maxima and minima, we want to be in the situation of this first domain here. This first domain, it had a global maximum and a global minimum, and these next two didn't. But these next two didn't for sort of different reasons. For the domain in the middle, the function didn't have a global maximum, and that seemed to be because the domain doesn't contain its boundary. We could get closer and closer to points that could be the maximum or minimum, but we couldn't actually plug those points into the function because they weren't in the domain. And for this domain, the function didn't have a global maximum because this domain is sort of humongous. It stretches infinitely in the positive x and y directions. So what I'm going to tell you about next is a statement called the Extreme Value Theorem, which pretty much says, as long as the function we're dealing with is continuous, and the domain doesn't have either of these issues, meaning it does contain its boundary and it's not infinitely big, then we're guaranteed to have a global maximum and a global minimum. So here's the statement of the extreme value theorem. If we have a function of any number of variables, and the important thing about that function is it's continuous, and the domain of the function that we're considering for this optimization problem satisfies the following two properties. First, the domain has to be closed, which is a word that means it contains its boundary. So it's not like that open disk from the previous example. And the second is that the domain has to be bounded, which means that it's not infinitely big. So if the function satisfies both of these conditions, then we're guaranteed to have a global minimum and a global maximum on the domain. And at first it might feel a little opaque. These two words, closed and bounded, take a while to get used to what they mean. Going back to the previous examples, if we're trying to figure out whether a domain is closed, well, that was the distinction between these two. This was closed, and this was not closed. And it turns out that, and this is just my little trick for figuring out whether a domain is closed or not, if a domain is defined using a less than or equal to sign, or a greater than or equal to sign, or an equal sign, then it's closed. But if it's defined using a strictly less than sign, then it's probably not closed. That doesn't always work, but it's a good heuristic. On the other hand, figuring out whether a domain is bounded or not tends to be a bit easier because you can just look at a picture of it. If it's something that you cannot draw all of on a single page, like this one, then it's not bounded. So this is not bounded. It is, however, closed because it contains its boundary. Its boundary is the positive y-axis and the positive x-axis. And again, it's defined using greater than or equal to signs. So that kind of fits into my heuristic. This middle domain, despite the fact that it's not closed, it is bounded. And finally, this one on the left is closed and bounded. It's not infinitely big. You can draw all of it on a single piece of paper without having to cut it off. Okay, so what the extreme value theorem says is if you have a domain that is closed and bounded, then you're guaranteed a global maximum and a global minimum, which is what we found here. Something you should be careful with, though, is it doesn't say that if a domain is not closed or not bounded, then it doesn't have a global min or max. For example, here, this domain was not bounded, but it still had a global minimum. In fact, you could come up with a function on a domain that was neither closed nor bounded, but that function still had a global maximum and a global minimum. So really what the extreme value theorem is all about is whether or not you are guaranteed to have a global minimum or maximum. Okay, so that's the extreme value theorem. And one thing to notice is that it doesn't actually tell you how to find the global minimum and the global maximum. So the last thing for us to do in this video is an example in which we use the extreme value theorem as sort of a guide for helping us find the global min and max of a function on a domain. So here's our example problem. We have a function f of xy equals 2x squared plus 3y squared minus 4x plus 5. We're trying to find the global minimum and maximum of that function on this domain, which is the disk of radius 4. So the first thing to notice is that the domain, it is a disk, and in particular, it's a closed disk. It's one that contains its boundary because it's written with a less than or equal to sign here. What that means is that the domain is a closed and bounded set, and so the extreme value theorem guarantees that we're actually going to be able to find a global minimum and a global maximum. So I'll make that as a note. But again, that doesn't actually help us find the global extrema. To find them, we actually have to consider a couple of cases. So here's a sketch of the domain. And looking at the sketch, there's sort of two different cases for where the global maximum and minimum could be. So in other words, we're going to break down this problem into two situations, which is the global extrema could either be on the interior of this disk, they could be on the inside, or they could be on the boundary. And the usefulness of making this distinction is that in each of these separate cases, we have different ways of finding where the global extrema could be. First, if the global extrema are on the interior of the disk, meaning if there was a point, say here, and this was the global maximum, well, thinking about what the graph of the function would have to look like here if this is going to be a global maximum, then this is also going to be a local maximum. So that means that if we were able to find the critical points of this function on the disk, then this point would have to be one of them. So in other words, if the global extrema are on the inside, then they're at critical points. And we know how to find those. We just take the gradient of f and set both components equal to 0. The other case is that the global extrema are on the boundary of the disk. In other words, they're points that maximize or minimize this function in blue that lie on this circle x squared plus y squared equals 16. Well, that just means that they're solutions to the constrained optimization problem where we're trying to maximize or minimize f subject to the constraint x squared plus y squared equals 16. In other words, we can use the Lagrange method to find them. So here's our strategy for this problem. We're going to do two separate steps, one in which we find the critical points of f that lie inside this disk, and another in which we find the solutions to the Lagrange multiplier problem using x squared plus y squared equals 16 as the constraint. We'll gather together all of the possible solutions that we get from these two steps, and those will be all of the possible candidate points for the global maximum and minimum. And in order to figure out which of the points is the global maximum and the global minimum, we'll just plug them into the function and see which one is largest. Okay, so again, the first step is going to be just to find the critical points of this function, and in particular, only the critical points that lie inside our domain. Remember, to find the critical points, we take the derivatives of f, and we set both of these equal to 0. And for this one, we find that x has to be 1 and y has to be 0. So the only critical point is 1, 0. Now, if we wanted to, we could do what we did in the lesson on maxima and minima and test this point to see whether it's a local maximum or a local minimum or a saddle using the second derivative test, but we don't actually need to do that. You'll see later that we're just going to compare the value of the function here to the value of the function at the other points that we find in the next step, and that'll tell us whether it's the maximum or minimum. Okay, so we're done with this step. Next, we need to solve a Lagrange multiplier problem where we're trying to find the maximum and minimum of our function subject to the constraint x squared plus y squared equals 16. So this is going to be our function g of xy. So to solve this problem, we always want to start by writing down the Lagrange condition, which would be that the gradient of f is lambda times the gradient of g. We need to compute these gradients. The gradient of f we actually already calculated. It's 4x minus 4, 6y, and that is equal to lambda times 2x, 2y. And so now we take this and we set up three equations, which are the x component, and the same thing for the y components. And then lastly, we need to use the constraint as one of our equations. Again, I like numbering my equations. You don't have to, but it helps me stay organized. 1, 2, and c. And now we just need to do some algebra. The first thing I'm going to do is I'm going to rewrite this second equation. I didn't get to talk about this in the previous video, but you want to be careful that you don't just divide by y and then move on. Dividing by expressions when you're doing algebra can get you in trouble because by doing that, you're ignoring the possibility that y is equal to 0, right? If y is equal to 0, then this equation is satisfied. But if you divide by y, then you might miss that. So a way to get around that is instead of dividing, we will rewrite this equation and factor it. So I'll take the lambda times 2y and I'll move it over to the left, and then I'll factor, and I'll get 2y times 3 minus lambda equals 0. Now, doing it this way, we can see that there's two cases coming out of this equation. There's the case where y is equal to 0, and there's the case where 3 minus lambda is equal to 0. So we need to consider those separately. So in the first case where y is equal to 0, we can go straight to our constraint equation, which tells us that x squared plus 0 is equal to 16, so x squared equals 16. And so x is positive or negative 4. And we found x and y. Remember, we don't need to figure out what lambda is in this case. So the candidate points that we get from this case are 4, 0 and negative 4, 0. So just a quick rewind. So far, what we've done is we took this second equation, rewrote it, and then this gave us two separate cases. The first case, we used the constraint equation to quickly find what the points are. Now, in the second case, we know that lambda is equal to 3. And so what we're going to do is we're going to go back now to the first equation, because that relates lambda and x. If lambda is equal to 3, then we have 4x minus 4 equals 6x. And now we can use this to solve for x. We get negative 4 equals 2x. And so x is negative 2. And to figure out what y is, we're going to use the constraint again. If x is negative 2, then this is saying that negative 2 squared plus y squared equals 16, which means y squared equals 12. And so y is equal to plus or minus the square root of 12, which is plus or minus 2 square root of 3. So I ran out of space to put the conclusion, so let me just bump this up. So finally, the points that we get from this case are x is negative 2, y equals 2 square root of 3, and x is negative 2, y equals negative 2 square root of 3. So we got 4 possible maxima or minima from these points. And the last thing to do is to take these 4 points and the 1 point that we found in the first step and compare the value of the function at all of those points. So here's a table that I've made. The points that we found were 1, 0, 4, 0, negative 4, 0, negative 2, 2, 3, and -2, -2 square root of 3. What we need to do now is take these 5 points and plug them into this function. So now that we've calculated these, we just need to compare them and figure out which is the largest and which is the smallest. Again, the extreme value theorem guaranteed us that the global maximum and global minimum were among these points. And now we can see that the smallest value is here at 3, so this was the global minimum value. And the global maximum actually takes place at 2 points. So there we go, we've solved the problem. So this has been a pretty good example of how these kinds of problems go. You need to find critical points of the function that you're given on the interior of its domain, if it has an interior, and you usually need to solve a Lagrange multiplier problem on the boundary of the domain. Once you've done both of those things, you compare the value of the function at all of the candidate points that you found, and if your domain was both closed and bounded, you're guaranteed to have found the global minimum and the global maximum among the points. So that's where I'm going to leave this video. You might want to review the strategy before you practice, but definitely practicing will give you a good sense for how this goes. Good luck with that, and I'll see you in the next one.